Hi, welcome back to Moose and Chemistry. This is electron configuration of the element gallium. Alright, so gallium happens to be number 31 on the periodic table. So for our atomic number, we're going to write a 31. Okay, its atomic mass number is going to be 7. Okay, there we go. There's that right there. Okay, so now let's look at this, guys. We have 31 protons, 31 electrons, and now our neutron count. Remember, it's going to be AMU minus the number of protons equals the number of neutrons for our neutrons, right? So we go 70 minus 31, and that's going to give us a total of 39 neutrons. Pretty darn snarly. So let's go ahead and put a 39 right there. Okay, so let's clean some stuff up here. And now, when we look at this, let's look at our electron configuration. Now, a couple things you have to remember in electron configuration is that the S subshell can hold 2 electrons, the P subshell can hold 6 electrons, the D subshell can hold 10 electrons, and the F subshell can hold 14 electrons. That's important to remember. Okay, also we're going to use the Orbital principle, which states we have to fill in the lower shells first before we fill in the upper shells, right? And easy as said and done, right? So we're going to use the diagonal rule to help us with that. So right here's the diagonal rule, and we're going to follow these red arrows down until we run out of electrons. So we just did the first one, 1s2, 2s2. See how easy that is? 2p6, and then 3s2. We just got to keep track of our electrons. So we need 31 of them. Come back to this, 3p6, 4s2. And then 3d10, 4p1. All right, if you count that up, 2 and 2 and 6 make 10, 2 and 6 and 2 make 20, plus 10 makes 30, plus 1 makes 31. Pretty darn cool, huh? So excellent. Now, guys, the next thing we'll do is we're going to do the orbital notation. Now, it deals with Hund's rule. Hund's rule clearly states that you put an up arrow in every suborbit before you start doing that down arrow in that suborbit. So let's do this. 1s, up and down. Pretty easy. 2s, up and down. 2px, 2py, 2pz, and then we go down. That's Hund's rule. Pretty cool, huh? Up and down. 3px, 3py, 3pz, and then we go down. Just easy as can be. 4s, up and then down. Now, 3dx squared minus y squared, 3dxy, 3dyz, 3dxz, 3dz squared. Watch this. 4, 5, 6, 7, 8, 9, 10. Now we only have 1 electron left, and that's 4p1. Yes, you have to have all those other suborbits with it, because remember, electrons have the ability to get excited, and they can jump suborbits or orbits. Pretty darn cool. So what about the noble gas notation? What's the nearest noble gas to gallium? Well, that would be argon. We put argon. You can't use the one after because it hasn't happened yet. So let's look at our valence shell. Here's our valence shell. So we're going to write this in numeric order. 3d10, 4s2, 4p1. Guys, this is awesome. What about our quantum notation? Well, the first thing is gallium is in the 4th period. So we're going to write a 4 here. So our principal quantum number is going to be 4. Our L value is going to be 1. Angular momentum is going to be 1 because gallium is located in the p block, right? And what's the magnetic number? Well, the magnetic number is going to be -1. It happens to be the first element in that particular row, right? So you're going to put a -1 here. And let's look at our last arrow. Our last arrow right there is going up. So that's going to be 1/2 positive for our spin. And that takes care of the Polyexclusionary Principle, which says that no two elements can have the same set of quantum numbers, right? So see how easy this really is? Electron configuration is totally easy, guys. So you guys be snarly, and we'll see you back here at Moosine Chemistry.